Increases, sir.
Increase of what?
Length, sir.
Increase of length. Suppose if you cool beyond its room temperature, what will happen? If
No changes, sir.
no
No
changes.
changes.
So now this temperature stresses are also called as a thermal stresses. Okay, so now you have two criteria here in temperature stresses. One is the calculation of temperature stress for a single component or a one component. Another one is it is made up of a compound bars. It is made up of a compound bars. Okay. So now let us consider a bar here. Okay. Let us consider a bar. Okay. So which is fixed at one end. So which has a length L here. It has a cross section area A. Okay. Cross section area A. Now consider room temperature as a T naught. Consider room temperature. Okay. Now if you heat this bar, okay, so if you raise the temperature of bar, okay, so let us go for you have raised to T2 degrees Celsius, okay, T2 degrees Celsius, okay. So now total temperature, rise in temperature, this is what delta T equal to T2 minus T naught, okay, T2 minus T naught. Okay, so to get the expansion or contraction of a member, what is the thermal property it has to get? ಹೆಂಗೆ ಎಕ್ಸ್ಪಾಂಡ್ ಆಗ್ತೈತಿ? ಹೀಟ್ ಮಾಡಿದ ತಕ್ಷಣ ಎಕ್ಸ್ಪಾಂಡ್ ಆಗುತ್ತೆ ಅಂತ ಹೇಳಿದ್ರಿ, ಕೂಲ್ ಮಾಡಿದರೆ ಕಾಂಟ್ರಾಕ್ಷನ್ ಆಗುತ್ತೆ ಅಂತ ಹೇಳಿದ್ರಿ, ಸರಿನಾ? ಯಾವ ಪ್ರಾಪರ್ಟಿ ಮೇಲೆ ಅದು ಕೂಲ್ ಇದು ಎಕ್ಸ್ಪಾಂಡ್ ಆಗ್ತದೆ, ಕಾಂಟ್ರಾಕ್ಟ್ ಆಗ್ತದೆ?
Sir, by applying pressure.
ನೋ ಪ್ರೆಷರ್. What are the important thermal properties of a material? Thermal properties, what are the thermal properties? Guess. Just guess it. Have you heard the name thermal conductivity?
Yes, sir.
So how are you going to define a thermal conductivity?
Heat carrying capacity of an object.
Heat carrying capacity of an object. Okay. Now, so in thermal stresses, so one of the important parameter which is going to affect the elongation or shortening of a body is what? The coefficient of thermal expansion. The coefficient of thermal expansion or thermal coefficient. Okay. So it is measured in terms of degree per unit length. Degree per unit length here. Okay. So now the possible case here, suppose you let us consider here. Now if you raise the temperature, okay, of this bar, it's going to get the new shape. This is what L naught. This is going to get the new shape L naught. Is it right? Suppose if you contract, if you reduce the temperature of this bar, it may reduce its length. it may reduce length. Now L0 is what? A final length. L0 is final length. Okay. So now let us find out the change in length after rise in temperature of value delta T, this is what? L0 minus L, this is equal to what? Delta L. Okay, this is what? Delta L, right? Now, so the expansion or contraction of the component is mainly in relation with the length of the object as well as the total rise in temperature. Length of the object as well as total rise in the temperature. Okay. So now, if it is raised by temperature delta T, okay. So change in temperature, now it is at delta T. Now change in length is what? Delta L here. Okay. Now, sorry, now this has to be change in. Okay, change in length. Okay, I have written a wrong here. Okay, change in length after rise in temperature. Okay, now this is what? Delta L equal to L0 minus L. Okay. Now what is the rise in temperature here? Rise in temperature delta T equal to T2 minus T0. Okay, T2 is final temperature. Okay, so T0 is ambient temperature or room temperature. Okay, or room temperature, right? Now delta L is what? A elongation. It has been caused because of rise in temperature of the value of delta T, right? Now let us note down. So the change in length, okay, or the deformation of the component because of rise in temperature. Now we'll say deformation of a component due to rise in temperature delta T. Okay, now delta L equal to, okay, delta L equal to alpha delta T into L. Okay, so where alpha is coefficient of thermal expansion, okay, so delta T is rise in temperature, okay, so L is what? Length of bar. L is what? Length of bar. Okay, so let us note down this equation as 1. Now this is what? A direct substitution. Okay, you can find out change in length if you know the rise in temperature and thermal coefficient and the length of the bar. Okay, now if you look out the bar here, this is what? Bar before rise in temperature. Okay, this is what? Bar after rise in temperature, right? Now if you does not go for restriction of this component, now it is going to take a free expansion. It is going to take a free expansion. Suppose if you restrict or if you restrain, okay, the movement of the elongation of the component then it's going to subject it some internal resistance. That means if you prevent the expansion of the component with the help of some support, then what will happen is going to subject it to some internal resistance. One more possible case, you can go for partial restraint. Partial restraint. So there is one more case. Okay, that is what one more case. Suppose now we'll take an example here. Now I have a bar here. Okay, initially it has a length L. L. So now I'll raise the temperature. Rise in temperature for bar. Rise in temperature of a delta T value. Okay. Now what will happen to this bar? Is it going to get the same length? Or length increases?
Increase.
It is going to make an increase. Okay. Now length is going to increase here. Right? Length is going to increase. Suppose now if you fix on both sides, now I'll fix on this side, right? And for this case also I'll fix on this side for reference purpose. Suppose if I fix on both sides, okay, and if I raise the temperature, what will happen to support A and what will happen to support B? What will happen at support A and what will happen at support B? Whether elongation goes on increases or elongation restricts.
Sir, transfer of heat takes place.
Transfer of heat takes place. Okay. Someone says it
Sir, restrict expansion.
transfer of heat takes place. Okay. Next. Next. You just observe here. Now, if you're not going to restrain the suppose let us take example. Now it is 100 mm. Okay, after heating it is going to cause 110 mm. It may get 110 mm. Okay, suppose what is the original length here? Original length is 100. Okay, new length is 110. Okay, so change in length is how much? 10 mm. Suppose if you prevent the expansion of 10 mm of this bar, if you prevent expansion of this 10 mm of this bar, so what is at support A and what will be at support B? ಏನಾಗ್ತದೆ ಸಪೋರ್ಟ್ ಎ ಮತ್ತು ಸಪೋರ್ಟ್ ಬಿ ಇಲ್ಲಿ whether it is going to sustain.
Sir, their length increases, sir.
Now
AB length.
these are rigid here. Okay, now these are rigid. Okay, now support A and support B are rigid here. Okay, now what will happen?
Break, sir. They will break.
What? Which one will break? Supports will break.
Sir, bar will break, sir.
Bar will break. Okay, so bar will break. One case. Okay, bar breaks. Now, as you resist the flow of the component, increase of length of component, what happens? So it's going to get some type of resistance here. It is going to get some types of resistance. Okay, so that resistance is what? Some stress is going to get over it. Some stress is going to get over it, right? Let us take an example. Now this is what bar before heating. Okay, this is bar after heating. Now I prevent this expansion of the bar. I will prevent expansion of the bar. Okay, now this length is what? L. I am going for same figure again. I am same concept, but little change in the considerations. Okay, now this is what L naught. Okay, now what is the change in length here? L naught minus L equal to delta L. Okay, now delta L can be calculated as alpha delta T into L. Okay, already noted this equation. Okay, next, if you resist the expansion of the component with the help of some restrictions, so it's going to compress this much of expansion. It's going to compress this much of expansion. So this compression causes some type of stress here. So now let us look out here. Now, how much distance you have compressed? You have compressed delta L. Compressed distance is how much here? This is equal to how much? Delta L. Okay. Now you just note down equation of extension and shortening. Equation of extension or shortening of a bar. So what is the equation? Delta L equal to PL divided by AE. Are you agree with this one? Are you agree?
Yes, sir. Yes, sir.
Now let us equate equation 1 and 2 here. Equate equation 1 and 2. Okay, so what will get? PL by AE equal to, okay, so alpha delta T L. Now I will write P by A as sigma T here into L divided by E equal to alpha delta T L. Now you just check it. So now temperature stress delta T equal to alpha delta T into E. You got this? You got this equation? Temperature stress can be calculated as the multiplication of coefficient of thermal expansion with the rise in temperature as well as with the Young's modulus, right. This is what equation to find out the stress in temperature stress in a component. So when it is completely restrained, that means completely constrained its expansion. What do you consider here? We have considered how much amount of length it has been increased. Okay, so that amount of length has been constrained here. Okay, so because of this constraints, it is going to be subjected some internal stresses here. It is going to be subjected some internal stresses. That type of stresses are called as a temperature stress. Right. So you note down delta T equal to what? That is the temperature stress. So E is what? Young's modulus of material. Okay. So alpha is what? Coefficient of thermal expansion. Okay. So delta T is what? Rise in temperature. Okay. So if you note down, this is what degrees Celsius, this is what degrees Celsius per unit length. Young's modulus is Newton per mm square. Okay. Now this is what coefficient thermal expansion. This is mm per degree centigrade. Okay. Unit length per unit degree Celsius. Okay. mm per degree Celsius or meter per degree Celsius. Right. So Young's modulus is Newton per mm square. Stress is also Newton per mm square. Okay. So by this equation you can calculate temperature stress. Okay. You can calculate temperature stress. Now, so if you want to find out the temperature strain, so what is the relation to get the temperature strain, or what is the relation to get the strain? Strain, how are you going to define? Someone reply. What do you mean by strain?
So result of stress.
Sir, it is the ratio of the stress by Young's modulus.
Now in this case, as we need to find out the temperature strain. Okay, so this is equal to what? Sigma T by E, right? Now this is equal to alpha into delta T, right? Alpha into delta T is what? The temperature strain, right? You got it? Okay. So now this is a case of completely constrained. Suppose if you constrain the partial expansion and partial restraint, so then you will get a different case here. Okay. Now let us note down for next possible case. This is what a partial constraint or restraint. If I given restraint. Now let us look out. So an member is fixed between two walls. Here, right? So some amount of gap is provided for expansion. Now let us go for this as delta. This is L. This is L. Now, what are the possible conditions here? What are the possible conditions if you raise the temperature of this bar? What are the possible conditions? If you raise temperature of this bar, right?
Increase length.
Increase length. Up to what extent it can increase?
Delta.
Delta. Okay. Then if you raise again temperature, if you raise again temperature, what will happen?
Break.
Break. What will happen? So now the possible failure in this case, it depends entirely on rise in temperature. Okay. So one possibility is here. It can come and touch here. Okay. If it touches, it has a chance to go for pre-expansion equal to delta L equal to delta here. Okay. Suppose if it has a capacity to extend beyond the delta value, then you are making its restriction. Right. So now let us go for the equations here. Okay. Now it has a possibility of expansion up to this much length, So now as we were given a chance to expand for whole length delta L, okay, whole length delta L. Now we just drop a line here. No. How much distance it has been prevented? So this much distance has been prevented because of the support. Are you agree? This much of distance has been ಇಷ್ಟು ಡಿಸ್ಟೆನ್ಸ್ ಎಕ್ಸ್ಪ್ಯಾನ್ಷನ್ ಆಗೋದನ್ನು ಪ್ರಿವೆಂಟ್ ಮಾಡಿತು ವಾಲ್. ಆರ್ ಯು ಅಗ್ರಿ ವಿತ್ ದಿಸ್ ಒನ್?
Yes, sir.
Okay.
Yes, sir.
Now,
Yes, sir.
what is the distance it has been restrained here? Whether there is a delta L minus delta equal to the distance restrained. You just look out. Up to this stage, it can freely expand. There is no any restriction, right? When you put the restriction, then it is going to get some resistance. That resistance is what is temperature stress, right? So now delta L minus delta, it is some value. Let us go for delta L1. Let us go for delta L1. Okay. Now the distance now in this case is possible to get the stress. Now let us note on delta L1. I will write here P L divided by AE. This is equal to what? Delta L minus delta. Okay? Delta L minus delta. So now PL by AE is the same. Now delta L, this much of length can increase because of rise in temperature. This is what alpha delta T into L minus delta. Okay? Minus delta. So now you can get the stress here. Stress is sigma T equal to, okay, sigma T equal to alpha delta T L minus delta, okay, into E divided by L. Okay. Now this is a stress equation in case of you have a partial restraints or partial constraints. If it is completely constrained, then you go for first case, that is what delta t equal to E alpha into delta t. Okay. Now, so this is what case of simple bar here. Okay, this is case of simple bar. Suppose if you have a compound bar, then you need to go for the consideration of shortening of one bar and expansion of the one bar. Okay. So let us note down problem here for temperature stress. Let us note down problem. Okay. Note down a steel rail is 12.6 meter. A steel rail 12.6 meter long is laid at a temperature of, I'll write here, a steel rail is 12.6 meter long and is laid at a temperature of 24 degrees Celsius. Okay. The maximum temperature expected is 44 degrees Celsius. Okay. 44 degree Celsius. Now, first bit, estimate the minimum gap between two rails to be left so that temperature stresses does not exist. Temperature stresses do not develop. Okay, do not develop. Now, second case, calculate the thermal stresses developed in the rails developed in the rails if no expansion joint is provided. Okay. Next, if a 2 mm gap is provided for expansion, if a 2 mm gap is provided for expansion. Next, third one, if the stress developed is if the stress developed is 20 megapascal, what is the gap left between the rails, Now take E equal to 2.1 into 10 to the power of 5 Newton per mm square, and alpha equal to 12 into 10 to the power of minus 6 per degree Celsius. So it has 4 criteria here. It has 4 criteria. That is what. So we estimate the minimum gap between 2 rails to be left so that temperature stresses do not develop. That means you need to leave the expansion of the joint as it is freely goes on. Okay, so it should not get in touch with any restrictions and to develop the temperature stress. Okay. Second case, they have 2 options here. One is calculate the thermal stresses developed in the rails if no expansion joint is provided. Okay, expansion joint is provided. If a 2 mm gap is provided for expansion. Okay, so what is the stress? Okay, what is the stress? Last one, if the stress developed is 20 megapascal, what is the gap left between the rails? Okay, what is the gap left between the rails? Okay. Now, now it is a rail structure. Okay. Now these are the conditions between 2 rails here. These are the conditions between 2 rails. Okay. Now what are the conditions? First, they have given the gap is, that means gap is there, sufficient gap is there. Okay, sufficient gap. Okay, so second case, no expansion joint is provided. Okay, no expansion joint is provided. Okay, so that means how much free length is there, that he has to be restricted. Okay, no expansion joint. Okay. So for second, a 2 mm gap is there. 2 mm gap is there. Okay. Next, fourth. Okay, if a stress developed is 20 megapascal, then what should be the gap? What is the gap? So just to try 5 minutes. Hello. Hmm. ಡಾಟಾ ನೋಡ್ಕೊಂಡು ತೊಗೊಂಡು ಲಾಸ್ಟಿಗೆ ಅದ ನೋಡು ಅದ ನೋಡಿ 4G ಮೆಟೀರಿಯಲ್ ಅವೆಲ್ಲ ಅದಾವೆ ಸ್ಕ್ವೇರ್ ಇಯರ್ ಚಾಪ್ಟರ್ನಾಗ ಅದ ಲಾಸ್ಟಿಗೆ ಅಷ್ಟು ಬರೋದು ಅಷ್ಟು ನಡೀತದೆ ಅಷ್ಟು ನಡೀತದೆ ಅಷ್ಟು ಚೇಂಜ್ ಮೈನರ್ ನೋಡ್ತಿರ್ತೀವಿ ನಾವು +or -5% ಭಾಳ ಚೇಂಜ್ ಆದರೆ ವೇಸ್ಟ್ ಮತ್ತು 600 ಬರ್ಬೇಕಾದ್ರೆ 300 ಬಂದಿಲ್ಲ 600 ಬರ್ಬೇಕಂದ್ರೆ 590 ಬಂದರೆ ಹಿಡಿತೈತಿ 610 ಬಂದರೆ ಹಿಡಿತೈತಿ So is there anybody done first case? So sufficient gap, no restriction of the constraints. So sufficient gap is there, then you can find out the first case, estimate the minimum gap required to between the two rails to be left so that the temperature stresses do not exit. Okay. So first case, all right, estimation of minimum gap. Okay, this is equal to delta L. Okay, so now delta L equal to what? Alpha delta T E. Okay. So alpha is how much? 12 into 10 to the power of -6 per degree centigrade. Okay, so delta T you find out 44 minus 22 equal 24. So it has a rise of 20 degrees Celsius. Okay, now E they have given. Okay, so that is what how much E? So 2.1 into 10 to the power of 5. Okay, E they have given. So now you find out what is the delta L here. 12 into 10 to the power of -6. Delta T is 20 degree. E is 2.1 into 10 to the power of 5. Now this value is in mm. So quickly calculate. ಎಷ್ಟು ಬಂತು?
Sir, 50.4 mm.
Sorry. Now this has to be L, not a E. Okay, this has to be L. Now we are calculating delta L, not a stress. Okay, so 12 point into 10 to the power of -6. Delta is 20 degrees Celsius. L is how much? L is 12.6 meter. Okay, Now it is what 12.6 meter. Okay. Now you calculate. How much you got?
.02 into 10 power minus 3.
Correct mado. Now 10 to the power of minus 6, 10 to the power of 3. You will get some cancellation.
3.024 mm, sir.
3.024
Mm.
Okay. Now this is what the minimum gap that has required to get the delta, that is what thermal stress as a 0 value. Okay. Next, calculate the thermal stresses developed in the rails if first case a expansion joint is provided, no expansion joint is provided. Okay. So that means now if you consider two rails here, okay, so the gap between two rails now it is how much? It is 3.024 mm. Okay. Now possibility of expansion is here. Okay. Now what they say in second case, first bit, there is no any expansion between the rails. That means they have placed one over another. Okay. So now you need to find out what is the stress it is going to be developed here. Okay. Now how much distance your restriction here? If you consider only on one part, you are making a restriction of, so now you are making a restriction of how much? I will go from this reference. You are making a restriction of 3.024 mm. Okay, 3.024 mm. Okay. So now if you restrict this to 3.024 mm, you are going to get the stress here. Now how are we going to get the stress? Sigma T equal to alpha delta T E. Okay. Alpha delta T E. Or you can calculate PL by AE, okay, because you know that length here. Now PL by E equal to what? Alpha delta T into L, okay, into L. Now P by A, it remains to, again we just cancel here, we are going to get the same equation, right? Now find out. Alpha is 12 into 10 to the power of minus 6, delta T is 20 degree, so Young's modulus is 2.1 into 10 to the power of 5.
Sir, 50.4 Newton per mm square.
50.4.
4
Okay.
Newton per mm square.
Now the stress which is going to induce in here, it is 50.84 Newton per mm square. Okay. This is what second case. Suppose if they give, okay, so a small gap between the two rails as a 2 mm here. Now this is what second case, second bit. Okay. What they are given, find out the stress if you gap of 2 mm is
Sir,
provided.
sir, 50.4, sir.
Let it be. Now you have a gap of 2 mm here now. Now find out what is the stress. Now you find out what is the stress. Now you can just refer the earlier diagram what we have noted here. Now they are going to allow free expansion for 2 mm here. Okay, free expansion for 2 mm. Now what is the distance it is going to expand? It is going to be restricted here. It is going to be restricted. Okay, so So 2 mm ಅವ್ರಿಗೆ ಏನು ಮಾಡ್ತಾರೆ, ಫ್ರೀ ಎಕ್ಸ್ಪಾನ್ಷನ್ ಕೊಡ್ತಾರೆ because they have given a gap here. But how much expansion is going to cause? Actually, it is going to cause 3.024 mm. It is going to cause the expansion. So you need to find out now what is stress you are going to get on this portion. Okay. So let us draw more clear diagram here. So now because of expansion, it has to expand 3 point, is it right? It has to expand 3.024 mm. Okay. But you are not restricting for this 2 mm. You are allowing it to freely expand. Okay. Now you need to find out what is the stress is going to get because of this portion, because of compression of this remaining distance. Okay. So to get it, you can go for this equation. You can go for this equation. Okay. Otherwise, you write it in a stepwise. You are going to get a difference of only 1 point or some distance here. Okay. So what is the distance it has to compress? 3.024 minus 2, it is 1.024 mm has to compress. So now you can write it for stress here. Okay. So now PL by AE equal to alpha delta TL. Okay. So now alpha delta TL you need to compress only for this much of amount. Now you can find out. Okay. Now 1.024, okay, into E divided by L. Okay. So now 1.024, 2.1 into 10 to the power of 5 divided by 12.6 into 1000. Someone calculate. How much you got? ಎಷ್ಟು ಬರ್ತಾವೆ?
16.25.
16.25 megapascal is the stress developed in the component when you have given expansion of 2 mm gap. Okay, when you have given free expansion of 2 mm, okay, gap. Next, last step. Okay, so what would be the gap you need to provide? Okay, if it is to develop the stress of 20 megapascal. Okay. If develops 20 megapascal stress, okay, so what should be the gap? Now you just observe here. Now look out here. Look out here. Now we need to find out a gap, this one. Okay. So now it has been compressed in a such a way that, so where it has exerted 20 megapascal stress, where it has been exerted 20 megapascal stress. Now how we can calculate here? How you can calculate? The simple formula again. Okay. So now PL by AE, okay, equal to alpha delta T L minus delta. Okay. Now in this case P by A they have given. P by A equal to 20 Newton per mm square. Now let us simplify here. Now P L by A E equal to alpha delta T L minus delta. Okay. P by A you substitute as a 20. Now what will get? Alpha delta T L, okay, delta E, or divided by E, sorry, this comes E here, E, now you will get a L here. Okay. If you simplify this one, you are going to get a value of delta. You calculate how much. You calculate how much. Otherwise, if you are getting confusion, okay, already you know the value of this one. This is how much? 3.024. You can just substitute it. And find out value of delta. Okay. I think you are going to get L also. You can multiply everything here. You can get value of this one. No need to transfer on this side also. So now 20 into 12.6 into 10 to the power of 3. Okay. So divided by 2.1 into 10 to the power of 5 equal to, so 3.024 minus delta. Now calculate delta. Right. This is how much? 3.024 minus entire this value here. So you provide attendance. You solve it. You provide attendance in chat box. So those who have given attendance, you go for next class.
Sir, answer is 1.824, sir.
1 point.
824.
Okay, right. So everyone given attendance?